Hello everyone. In this video, I want to talk about basically a question that was asked, and it's very common in my computer-aided engineering class when we did a stress analysis on a simple I-beam that is cantilevered and there is some load on the top. And the question is about the stress distribution and specifically about this max stress value based on which many people go ahead and do the design, right? So in this part, if we look at it, we see that the maximum stress, so here I apply the 1500 Newton load on the top surface. I fixed this back end and ran a simple analysis without changing the default mesh size. And this is the stress plot that I got. This is the 1 Mises stress. And if you look at this, you probably would see that this should not really be matching the ideal or theoretical case. And this is a simple problem that we have theoretical solutions for it. As you know, the maximum bending moment happens at this edge, and the maximum bending stress happens at the top or the bottom, depending on the sign of it, positive or negative. So you expect, first of all, the maximum stress to happen here, not a little bit away from that. The second thing is, if you look at this areas of high stress, you clearly see discontinuities, right? It's not a smooth transition. And here you go from yellow, orange, red, and then go back to yellow. That does not make really much of a sense, this sudden increase and then decrease after that. That is an indication that the mesh size is not good enough. By the way, what is the mesh here? Can I show the mesh? Can I overlay the mesh on this stress plot? Yes. So if you right click on the stress, you don't see the option here, but if you right click on the legend, you can see the option for show mesh. So here is the mesh overlaid on the stress result. And one other thing I want to mention before I go to answer that question of is this good or is not, and then can we trust this maximum value and report it, or the safety factor that comes with it. Before that, I want to mention one thing. If you look here, the stress values at these nodes, at these vertices, they are not all the same, correct? You see that here I have some value here, I have some value here. You can see different colors, right? You can always right click on the probe and you can basically probe on those locations. But you clearly see that what we are seeing here is what we call a stress at nodal locations, at nodes, and they're different, okay? This is one way to see the stress. Another way, another option that you have in stress, if I define a new one, look, if I go ahead and define stress plot, and then this time I still do the 1 Mises, but I go under advanced options, and instead of node values, I say I want an element values. Okay, and I okay that. Now look, here you see that the value of a stress is the same all over that tetrahedron element. Okay, of course, going from one element to the other is different, but all over the elements, the value is the same. So this is what we call basically unaveraged or element-wise stress distribution. This is the nodal one. Okay, this one. Let me, guess I clicked on the, let me bring this down. Clicked on the right thing. Here. So this is node by node. This is the element. Now the difference between these two is what we call basically energy error. Okay, so let me show you that one as well. So if I right click again and say define a stress plot, and this time instead of 1 Mises stress or maximum normal or anything, I go to this guy, energy norm error, ERR, and say give me this one. And you get that. And if you see the high values in this energy norm error is when the difference between the nodal values and the element values is high, right? In these regions, correct? Look, in these uniform regions where all nodes are green and the average of the element is also green, you will see very small errors. But in these regions, right, where look here, look at this element and this one, it changes anywhere from red to yellow to orange. But if you look here, these two are red, that one is yellow, right? And then this one is orange. So when this discrepancy, the difference between nodal and element values is high, or in other words, another way to put it is when the discontinuity of this result is large, that is an indication that there is high error over there and the mesh is very coarse and you have to refine the mesh. So before I talk about how to refine the mesh and everything, let me attract your attention to the help from SolidWorks that explains exactly how it gets these nodal values and the element value basically. So it says each element has a bunch of nodes, which are the connection points to the other elements, and some of these internal points called the Gauss points. And when SolidWorks solves for displacements and then strains and then stresses, the stresses are calculated at these Gauss points actually first, then they are calculated at the nodes. It's not the other way that you might think that first the nodal calculations are done. Actually here the Gauss point values and the stresses at the Gauss points are calculated. And then how do you get the nodal values? So here, let's say I have some values from these different Gauss points, and then look at this node based on the contributions from each one of these Gauss nodes based on the distances they have to this node. So I get the value of 2 from this guy, a 3 from this one, a 3 from that, and a 6 from that. And you see this is 6 because this is much closer to it. And then if I average these, right, I get 14 divided by 4, I get a 3.5, right? And similar things for other nodes. So the contributions for the stresses from these Gauss nodes at each node is taken, added and taken an average of, and then you show those nodal values. And clearly you see at each node you're going to have different values, okay? So this is the nodal values. Now, on the other hand, if you want to show element-wise, so here, look, if you look at this element, so this is just one face of it. By the way, when I say elements, this guy is not one element, okay? These are several elements, and this is a 2D thing, not a 3D, but you can assume that like this is a 3D problem looked from the top view. But each one of these triangles is an element. So now, look at here. This is how you calculate a single number per what? Per element, as opposed to here a single number at each node, at each corner. Here we have one single value from what? From the element. How? Here you average the Gauss point within the element. So here if you have 3 Gauss points within this element, 1, 1.2, 1.7, you average them, you get 3.9 divided by 3, you get 1.3. Okay, so internally here, you take average of the Gaussian points, you get one value for the node, but when it comes to nodal things, you get it from Gauss points that are surrounding that node, and because this node belongs to several elements. So you have to get values from all of those elements, not within one, and take the average, okay? So this is how you get what? Nodal values as opposed to element values from those Gauss values. And the difference between these is what we call the basically norm error, right? So this is that energy norm error. And if you look at here, you look at the maximum value of it is a percentage. These numbers are all percentages. So the maximum percentage is about 48%. So here at the red spot, which is right down there, you have about 48% error, or a lot of discrepancy or discontinuity between the nodal and element. Okay, and that's not really a very good and smooth transition, as you can see. So now, how do I refine the mesh? One way you might say, well, I just go there locally and I try to apply a mesh control, right? So I right click here and then I say I want to apply a mesh control. So you right click, apply mesh control, and then you come here and let's say you pick these areas, these edges, these areas of stress concentration, internal edges and so on, and then you make it a finer mesh, okay? And then would you get to the result that you want? May or may not. You might need to make it finer and so on until you get that energy of the norm to be basically smaller. So is there an automatic way to do it without you keep trying and finally maybe getting there or not? Is there an automatic way in SolidWorks to refine the mesh and get it fine enough so this plot is much smoother, you don't get these discontinuities, and you can trust those maximum stress values? The answer is yes. How? You come here, right click on this static and go to properties. Then you go to adaptive. You see right now there is no adaptive, but you can do H adaptive or P adaptive. H adaptive means reduce the size of the mesh until the discontinuity is below so much, okay? P adaptive means change the order of the element. Do not reduce the size of the element, but change the order. Instead of a linear element, where the mode shape is a linear function, right? Make it a quadratic, make it a third order, fourth order, and so on. So here you increase the order as opposed to reduce the size. So let's say if you want to do an H adaptive and you want basically some target accuracy. So let's say I want to go to 99% accuracy. And then how many loops, how many times do you refine the mesh? So here, let's say I want 5 loops to go and refine the mesh until you get to the result that I want. And then you can also activate this guy called mesh coarsening, which is basically in the areas that discrepancy was very small, that discontinuity was very small. Go ahead and reduce the size, number of elements, or make the elements bigger so that the total runtime is not really super large. So you can activate this item as well. And okay that. So now look, I run the study again. It's going to do it 5 times. And it's going to refine the mesh each time until it gets to some desired result. So look here. By the way, one of the things you have to do is, look, when you want to do an adaptive mesh, you cannot do the blended curvature. You have to do pure curvature bed measure, okay? So if it gives you this error, the way to fix it is you go to the mesh, right click, and then go to basically create mesh here, and then go down here to mesh parameters and change this to curvature based mesh, not blended. Okay, so now it should be allowed to get the job done. Let's see. So we run it, and you see here, solving H adaptive, loop 1 out of 5, 2 out of 5, 3 out of 5, and it takes some time, but it adaptively modifies the mesh to get you much better results. So let's take a look here. Okay, so we did our 5 times, and now let's look at these stresses. Look here, let me get rid of the mesh. So this is now the basically this one should be element wise, right? And this one should be nodal wise, just nodes. Look at that. Remember, you had all these red patches here and they were not even continuous. Now look, you see? It's much, much better. It's much smoother. And you see a very smooth transition here. Rook, blue, then those numbers. Okay, so you see it's much smoother now. And if you look at the energy norm, look, this is down to only those few spots of 20%. And those are these corners that you have basically some numerical calculation errors. Okay, so here you can see that uh, if you look at the element wise versus nodal, you see there is discrepancy here. There is difference. And remember, it's always important to basically be inspired from the theory. Don't just rely completely on the software. That's the worst thing that can happen for engineer, is to leave their knowledge aside and just run some numbers and put some numbers in the machine and get some numbers and trust them. So remember, this is a simple 1D problem, and you expect the moment to linearly increase, get to the maximum at this very edge. So at this edge, you should have maximum stress, which you see right now you do. And then nothing here is in this Z direction is different. So when you move here in the Z direction and you go from these green values all of a sudden to a red hot spot, that is an indication of a numerical problem. Okay? And I want to show you another thing that can indicate that whether there is some numerical problem or not, right? So here, if you basically make the mesh smaller, right? So here, if I go ahead and remember the mesh, it was like this, correct? Now, if I go ahead and make it even smaller than this, make the mesh even smaller than this, or bigger than that, what would happen to the values at specific locations, right? So for instance, if I look at this green region, right, this middle region, you see the stress is around 3, 4, 5-ish, kind of 10 to the 7, so 30, 40 megapascal. And this high point is about 70, correct? So this high point is 70, this green area, and this kind of turquoise area, right? Or yeah, probably that's what you call them. This region is about 20 something. Now, if I go ahead and make the mesh much coarser or much finer, what would happen? So here I bring this from this middle to this coarse side and make it a very coarse mesh. Let's first look at it. You see, now it's not even locally controlled, although I can locally control that a little bit over there, right? And let's just apply a local control over there, here. So now I have smaller mesh elements close to that surface, and then bigger elements elsewhere. And you see the total elements are much, much bigger than last time, right? So if I go ahead and run this, let's see what you get, right? We're going to look at the same region and look at this stress here again. And look at this region. Remember, it was around 20, 30-ish. Now here we are in this yellow region, so we are still in 20 to 24, correct? You can always probe it. Correct. So let's see if I can probe something here. Right, you see 22, and last time it was something similar. How much was this max? Look, right now it's about 30. Last time it was 70. Do you see? So I made the mesh bigger. I'm around 21, 22. My max is 30. If you go back and look at the video, just move back a little bit. The same region with finer mesh, this was still around 20 something, but this hot spot was around 70. So you see that the values in this around this edge is converging. It's coming to some 20 something values, but in those areas of numerical error, it is not converging. It's getting to bigger and bigger numbers. It jumps from 30 to 70, right? This is another mesh size. I made it a little bit smaller, not as small as last time with adaptive. Here I'm running with no adaptive. And again, look here. I made it a little bit smaller. And again, if you probe, look, in these regions, if you click on it, look again, 24, 28, 29, stuff like that, right? 25. But now, how much is it? 40. And it went up as high as 70. And even you can go higher. You see? So in this region, I should expect about 20 something. This is my maximum stress, 20 something. And in that region where it's very, very what? Very high, an outlier, it jumps. That is not the actual stress that I should be reporting. So hopefully I could answer those questions and make it clear where to look for those singularities, why, based on the theory, based on these basically energy norm errors and so on, and the difference between nodal and elemental values, and to make the results better, maybe adaptively, and get results that you can trust more and do a better design for. So hopefully the video was useful to you. I'll see you in the next lecture. Thank you.